Hello, I'm Dr Avice Hall and I'm a plant pathologist. I'm semi-retired, based at the University of Hertfordshire. In 1963, a man called Van der Planck, and as research students we always called him Van der Floorboard, but that's another case, he suggested that plants had two plant defence mechanisms, and in those days he called them vertical resistance and horizontal resistance. And he suggested that the vertical resistance gave resistance against specific, even races of plant pathogens, but that the horizontal resistance actually gave some resistance against all pests and diseases. Remember that. Because there have been masses of development since then, and so on and so forth, and we now describe active plant defence pathways and passive plant defence pathways. And silicon comes in, as you will see from what I'm telling you, in the passive. So I'm very quickly going to talk about the active plant defence pathway. I won't say it doesn't interest me, but this is the thing that everybody's doing the research on. What elicitor is there, what's the resistance gene, how's the reaction going, and so on and so forth. From my perspective, it's brilliant. I can glory in it. It's fantastic. However, it never reacts until the pathogen is in the plant or on the surface. And that is very different from the passive or constitutive pathway, and it's been developed and it's morphological. What is the plant structure like? How does the plant structure protect the plant against pests and diseases? And I just remind you, every single plant on the planet, every single species has pests and has diseases. Wild, tame, you name it, there are diseases. That's why plant pathologists have always got a job. But our problem from the point of view of agriculture and horticulture is we put them all together. We have monocrops, and the pathogen or pest says, wow, this is a wonderful place. I can grow and reproduce in vast numbers. Nothing can stop me, perhaps, etc. And that's why this morphological effect is really, really important. Because if the pest or pathogen lands on the plant, and for some reason it's not such a nice place, he's a bit uncomfortable if he's a pest, etc., then he's deterred, he doesn't eat as much, or she doesn't eat as much, and therefore she doesn't reproduce, and therefore you get lower numbers. So this morphological thing is really important, and it's effective against pests and diseases. It includes wax and cuticle thickness, cell wall thickness, leaf hairs, phenols, all those sorts of things are there in the plant. And actually they are protecting the plant. However, it's polygenically inherited, and I suspect that over the years in our plant breeding, we've taken notice of everything else. I'm afraid I've worked mainly on strawberries, and it's certainly true of strawberries. We want size, flavour, ability, to pickability, and the lot. And then you think, oh, it's got this disease. What should we do? And probably some of the morphological has just disappeared over time. But it could provide a very useful tool. I do believe you should have a multifaceted approach. I don't think we should put all our trust in one thing. And I suspect that, biocontrol can work ever so well for insects, even in strawberries. and so on. I'm not decrying. It's not much good for fungi. It's really hard to actually get the balance right and to get the compounds. I mean, there are some useful things, but it's not universal. I think that soil health is important. I think nutrient is vital, but I also, I was discussing with a researcher the other week, and he had heard people say, if we get perfect nutrition, we won't have any disease problems. And I said, good heavens, that's a bad idea. I'm sure we will. And he said, oh, I'm so glad you said that, because that's what he thought as well. So it's really hard just with nutrition to have no diseases. And I think the point about silicon nutrient, which I hope I will show you, though admittedly mainly from strawberries, for which I apologise, is at the very least, they enhance the passive defence pathway. So, silicon nutrient, I think it must be considered as a nutrient. There's all sorts of legislative difficulties if it's thought of as a pesticide, regulation, heaven alone knows what all. And I was deeply attacked a few years ago at Fruit Focus for having the wrong word on a piece of literature that would make it illegal. So please, friends, it's a nutrient, and it should be thought of, or it shouldn't be thought of, as a pesticide. Not even a physical pesticide, though it might be. So I'm really trying to be careful not to get myself in trouble legislatively. So you can read masses about silicon. They've used it in rice since 1947. There's vast amounts of research on silicon. However, it has to be bioavailable. Sand is no good. You have to have the bioavailable, and it's reported to have, well, it's reported to be almost like a wonder drug. It affects morphology, cuticle thickness, etc. It increases the number of plant hairs, I'll demonstrate that, but also increase in yield, etc. Or the sort of mantra in the academic papers, it's against abiotic and biotic stress. But when you look, not that much is quantified. And when we started to use it on strawberries, one of my aims was that we quantified it. So we were walking back from a strawberry trial that we're going with a brilliant grower who really kept me, you know, you can't do that, mate, on a farm, you can't do this on a farm. So it was absolutely brilliant. And as she walked back, she said, why do we get better control of strawberry powdery mildew, which is the big disease everybody's worried about, if we use potassium bicarbonate? They use food-grade potassium bicarbonate as a sort of protectant fungicide, but she said if we use it in a silicon spray, or silicon wetter, I think was her words then. And actually, I had to admit, I knew nothing. I didn't know why it was more effective if it was in a silicon wetter. And since then, we've done glasshouse field trials, which I'm going to tell you about, so that you can understand a bit. So, what I'm going to do now is tell you a little bit about our strawberry results, which I think will interest you. Here you have on the farm, on a commercial trial. I mean, on a commercial farm, all the strawberries were sold. So here you have a classic epidemic. Every plant pathologist loves that, every grower hates it. This is the line of strawberry powdery mildew when it was in the fertigation. We're applying it in the fertigation, depending on the trial, either once or twice a week, and so you got that reduction. And this was where it was, where we were using fungicides, which was fine, and actually, though not quantifiable, where you had fungicides and silicon nutrient, then the disease was even lower. So actually, that was very interesting. This one may look a bit odd, but this was the next, if you like, breakthrough. This shows you 2 spotted spider mite, a major pest of strawberries, and it shows you that if you're using silicon nutrient, you have very low numbers. What was amazing, and this goes to show how everything integrates with everything else, what was this enormous peak? What was that enormous peak about? Why all those 2 spotted spider mites? Well, we sat down with our heads in wet blankets and talked about it, and we realised what was happening. They were using entirely a fungus as a biocontrol for 2 spotted spider mite. Really interesting. However, they were also, on some of the parts of the trial in the tunnel, they were using fungicides to control the strawberry powdery mildew. And we did it 2 years running, and I'll show you those results in a minute. The bottom line was, for biocontrol with a fungus on 2 spotted spider mite, you actually want the fungus to reproduce and have its own little epidemic, don't you? But actually, if you're having to use fungicides to control your strawberry powdery mildew, then actually you are preventing your biocontrol working. But with the silicon nutrient and no fungicide, you still got control of the 2 spotted spider mites. And interestingly, a former student, when we started work on strawberry powdery mildew, even earlier, a former student who was running a biocontrol company said to me, Avice, whatever you do, they must think of everything. I just get the biocontrol right, and somebody comes in and puts on a fungicide or even sprays sulfur dust, everything dies. So seriously, it's a really interesting interaction. And the next slide does show you here, it's all statistically significant. So the strawberry powdery mildew is greatly reduced, and the 2 spotted spider mites, all just with a silicon nutrient in the fertigation system. Now, the other interesting thing, this was an early discovery, and I had no idea what the, how can I put this, the benefits of this were. When you are using silicon, you actually get more hairs on the strawberry leaves. Bit worried about whether you got hairs on the strawberry, but we passed that test. We didn't. So we get both more hairs and longer hairs. Again, statistically significant. So the summary so far is reduction in strawberry powdery mildew, reduction in 2 spotted spider mites, and by this time we knew we had an increase in leaf hair density and leaf hair length. Remember, that was part of the passive defense pathway. Was anything else happening? But why or how? How does two-spotted spider mite feed? Well, a very famous entomologist in Britain, Ian Denholm, said, oh, that's quite easy. They feed like this. This is powdery mildew penetrating wheat. We've got no sound, sorry. But just watch, it's brilliant. So this is the aprosorium, and then you get the penetration peg, the enzymes are coming out, exerts enormous pressure, push, push, push. Through the cell wall, into the cell, form the hostorium. There's the hostorium, accept the nutrients. So, should we try again? Note enzymes, note pressure. Yeah. Just watch. It's really dynamic. So, elongating secondary hyphae, formation of the aprosorium on the surface, penetration peg begins to go in, enzymes, that's little red dots, and pressure. Through the cell wall, wow. So, interestingly, if you look at electron micrographs, you can see the effect of that. The cellulose fibrils that make up a cell wall are actually rounded at the ends because of the enzymes that have degraded it. But there's also, you can see the pressure down. What I say to students, and I think you'll like this illustration, imagine a nice parquet flooring. Imagine a really fat lady in really high heels who has inadvertently stepped on some acid on her way to the party. What will she leave on the parquet flooring? Lots of little holes. That's exactly what these fungi do. Exactly. It would be similar for an aphid in the sense that they pierce through the cell wall. Okay, so it doesn't quite do our, you'll see, we'll get to our two-spotted spider mites in a moment, but they're going in directly. And the plant's morphological defences perhaps are not enough.
Can I just ask?
Yes, of course.
Happy to be stopped with.
Yes.
When the lower image in that photograph of the sort of ghostbusters sort of blob, is that similar to like the stripy effect that we see on the leaf? Because with mildew, we tend to associate more a pustule on the leaf, don't we?
I can probably show. Powdery mildews are really, really interesting because the spore, and it's just the same for barley powdery mildew, wheat powdery mildew, oats, rose powdery mildew, the lot. They have what we call elongating secondary hyphae over the surface, and they just penetrate individually to get nutrient, and then they indulge in their asexual reproduction and produce the conidiaspores which go and cause trouble. They are discrete lesions to start off with, because that, evolutionarily speaking, every spore needs to penetrate and grow. But then over time, they may coalesce. So you have got an individual pustule to start off with. And you may remember when we're assessing disease or you're doing the National Cereal Leaf Survey, which I've done, you not only look at the amount of disease, the percentage disease cover, but you often look at the green leaf area remaining, because it's the green leaf area remaining that's different. If you think though of rusts, that's a bit different, because the rusts have their hyphae actually in the cell, in the plant, and going between cells inside the plant, and wonderful mycological word, they're sometimes said to be erumpent. So they erupt from the surface. I've never looked up erumpent in a dictionary, but I don't know how they describe it. But and those are also individual lesions, but they're supported by hyphae inside the plant rather than hyphae over the surface that are putting things down. Rusts still have hostoria. They still have to go, they still have a bit of an active entry into the plant. Anybody got any other comments or questions?
What is the time scale of that under ideal conditions?
Okay, very interesting question. I can't tell you for powdery mildew because for wheat or barley, but I know absolutely for strawberry powdery mildew that it's 144 hours of the right temperatures and humidity. And from that, we've got a forecasting system, which I can tell you about sometime. But in other words, the environmental conditions have got to be perfect. And for powdery mildews, it's usually only a certain humidity, 60-70%, and a certain temperature, 18-20% degrees, okay? And the fungus will grow whenever the conditions are right and stop when they're wrong. So on our strawberry one, this is interesting. These are hours, and these are days, and these are numbers of hours. And each green line is this is the end of a season, is an hour. So you can, I'm talking to my, so here the conditions were quite conducive to disease. Here they were less conducive. The hours accumulated more slowly, and then here they were faster. And we use that in strawberries to predict when when fungicides are needed. And that way we've halved the number of fungicides that are used. But it is specific, and some other diseases like septoria, you've got extra parameters because septoria is rain splashed, isn't it? Botrytis in strawberries requires free water and so on. So a very good question, but that's one of the things that people have worked out for almost all pathogens. And the bottom line is, if the fungus likes the conditions, it will grow. And if it doesn't like the conditions, it will stop. Which is why we have different, we have different disease levels in different seasons, don't we? So, but it's ours, rather than, for most things, rather than days or weeks. Okay. So, back to silicon nutrient. So here are some electron micrographs of the leaves of strawberries where there's been root application of silicon, and this is the times 5,000. And so this is the control. This was no silicone application. And I think you can see that the lines in the wax are quite far apart. But as soon as you get the silicone, then the lines are closer together. The wax is more lumpy. And when you go to the next slide, this is really interesting. There are all the proper measurements on here, but this is without silicone. And you will see that the surface is comparatively smooth, and there are just a few hairs. But if you look at the one with silicone, can you see that not only is this part all thicker, but can you see you've got these incredible mountains, as it were, on the wax? Now, those are what we call phytoliths, or put it another way, it's silicon crystals. So it's all crunchy. And we think this is why, one of the reasons why the two-spotted spider mite is deterred. They don't like this crunchy surface. They don't like this crunchy surface. It's as simple as that. And if there are more hairs, they don't know. But even the powdery mildew, you know, the penetration peg would have further to go. You can germinate powdery mildew spores on anything, but they can't penetrate if there's, you know, if you see what I mean. So if you know, if it's like this and it goes in, that's fine. But if the germ tube comes along and it's all crystalline, it might be swinging above the surface and just not get there, because remember, it's all microscopic. So this morphological change is what gives you your disease and pest control.
Is that a copy of the original plant passive system, or did the plant actually have a silica system before?
Do you know, that's a really good question, and I haven't referred to it. All plants require silicon. All plant hairs are silicon.
Would the addition of silica to a plant's natural silica, though, affect its ability to photosynthesize? If it's got this crunchy layer?
Do you know, that's really interesting. I didn't think of it like that, but I've measured the chlorophyll, and a lot of species of plants have more chlorophyll with silicon. Even wheat. I've stood in the field myself and measured it.
Maybe it has a magnifying effect on the leaf.
I wouldn't think in that way physically. What I'm not talking about at all is all the possible physiological effects that it might have. I have never had enough money to be able to do research on how the chlorophyll is enhanced by things. It is true, if you spray too much silicon onto a plant, you will have an adverse effect because the silicon will deposit out on the leaf surface. I'll talk a little bit about that, but all this was done with root applications. And I will talk about that. But yes, all plants require silicon.
Is there a link between silicon and magnesium? Because magnesium and chlorophyll are linked, aren't they?
Good question. I've never got any satisfactory answers. We have done hydroponic experiments with strawberries and changed particularly potassium and magnesium. But in the strawberry context, I think we changed I think it resulted in changes of EC, which were detrimental rather than actually finding out. There's definitely a link, and there's definitely one of the things that's reported about silicon is about it'll enhance mineral uptake and that sort of thing. There's a massive research. I think the difficulty is quantifying it and, you know, working it out. It is generally beneficial. Now, this doesn't seem to have come. Oh no, it's okay, it's okay. So, what is it doing in the plant? Look at the surface, what's happening in the plant? Well, I want you to imagine, because I'm a bit passionate about root application, it's gone in through the roots where there is a silicon transporter gene. In other words, the plant, this is wrong philosophy, the plant knows it needs silicon. It's ready to take it up, okay? It then moves through the plant in the xylem, like all water, etc. But when it gets to the leaves, it's deposited, and I think that must be a concentration effect as a result of evapotranspiration. So when it gets to the surface of the plant, you know, the moisture is evaporating, isn't it, according to the weather, and it's then deposited. So the question is, where is it deposited? And in here, I hope you can see, we've got this is wonderful molecular tracker dye, which glows bright green and fluorescence under the microscope. What a pleasure. But can you see, that's your upper cuticle, glowing green. That's your lower cuticle glowing green. We think that was probably a stomata. But can you see all these palisade cells have all got silicon deposited in them? It's not the best. I have got a handout which you can take. It's not the best thing, but it is vivid. It really is. And here you have without silicon, with much fainter, lower, and virtually nothing on the upper surface. And interestingly, if you get your microscopy right, you can actually measure the intensity. And so you can get a physical measurement of how much glow you've got. And that, you know, you can do your statistics if you're that keen. And you can show that with the silicon, you've got more silicon in the plant than there. So, deposited in the leaf, remember that penetration peg? It's got a really hard time. And then, where else is it deposited? Well, in strawberries, it's very clearly deposited in the petiole, in the xylem. So again, get that picture, it's going up through the plant and the concentration must be increasing, and so it's deposited in the xylem. But remember, because of the transpiration stream, it will be going to all the plant parts that are developing. And so the beauty is, if you're applying it regularly, it will go into all the newly developing leaves. And so on. And once it's there, it doesn't move. Okay? Once it's there, it doesn't move. It stays there forever. Okay? Now, this next one does confirm what I think. This was done in a pot, okay? This was done in a pot, and when the silicon was applied to the medium in the pot, it deposited in this xylem, but here is just a cross-section of a root. The pale green is the amount of silicon that the plant had got anyway. What is really, really interesting is when we were working actually on the farm, in the tunnels, and applying silicon. We got all the deposits in the leaves. We never got them in the roots. And my conclusion from that was, well, in a sense, we didn't need it in the roots, but that what we were giving was always going up and being spread. Moving in the transpiration scheme. So how does silicon reduce susceptibility to strawberry powdery mildew and two-spotted spider mite? The hypothesis is that the cuticle and the thicker cell walls of the epidermis and in the palisade cells inhibit the penetration pegs of things like strawberry powdery mildew and so on, or any other powdery mildew on any other plant, and that those phytoliths on the surface, they inhibit the two-spotted spider mite, and the increase in density of the leaf hairs is inhibiting possibly the strawberry powdery mildew, but definitely the feeding of the two-spotted spider mite. And so the use of a bioavailable silicon nutrient through the season enhances the passive defense pathway and so reduces susceptibility. I do think for something like strawberries, it's regular use. So, it's me again. This is just a picture of, you know, what it looks like to be a bug. Gives you some idea of how uncomfortable it might be if you'd got phytoliths and everything else. Other effects in strawberries that we have found, some of which you will see we've replicated elsewhere, is greater biomass, enhanced chlorophyll, increased yield, earlier flowering, greater production of runners, a mixed blessing, unless you're a propagator, when you might like it, or, and we've seen it on all cultivars that we've tested. And we've basically used mainly what the growers were using.
If it's immobile, once it's deposited, so in other words, you need to apply, as the plant is growing, you should be applying it to inoculate, if you like, the new growth. Is that right? Is that?
Yes, you would. I suppose this is a bit like a flu jab. In other words, you need the silicon in the plant before the pest or disease arrives. So it's not. It's got to be there.
It needs a constant top up as the plant grows, really.
Yes. Now, of course, the really, really interesting thing to speculate on is strawberries grow continually, don't they? Wheat and barley and so on are, I forget the correct botanical term, but they're definite, aren't they? When you've got the flag leaf, they don't grow anymore, and then you've got the the development of the ear and so on. I'd say two things. If you were applying it early in the season, you might prevent diseases that start at the bottom of the plant and move up, like septoria. But in a sense, that silicon is wasted eventually because the leaves die. So you have to do something for the top, and that could be a moment when, having applied originally in some root application, you could do some sort of spray that would have an effect. Now, I have got a slide here about should you spray or should you do root application? And of course, the answer is I don't really know. What I will say, though, if it is travelling throughout the plant in the root system, from the roots to the shoots, and if you've got it's moving in the transpiration stream, and if you've got these silicon transporter genes, in the roots, then it does make a lot of sense to apply through the roots.
Don't forget in arable we don't irrigate on a regular basis.
Precisely. However, George, is he here? What do you advise, very quickly?
Well, we advise actually applying it in a seed trench if you can, and then apply it as a foliar as well later on in the season. So
exactly. So we haven't, you know, I think there are forms. I think it's worth thinking about. I've not done the research. I think spraying is perfectly acceptable. It certainly has a beneficial effect on wheat, and I'll see that. You'll see that again later. But I think what you've got to think about is it won't enter the plant. So you will be using it like an old-fashioned non-systemic fungicide.
I've got to disagree with that one, I'm afraid. I do know that if you use it as a wetting agent, as a modified trioxylane, yes, you're right, it won't go into the plant. But I am assured, and I've got a lot of work, whereas if you use them as silicon dioxide, it does enter the leaf.
I'm not saying it doesn't enter the leaf. I think it all does enter the leaf. But there are not the roots in for it to be transported round the plant. That's my point.
So we say the spray is like furniture polish, as in once you hit, it stays there, but then doesn't translate.
Yeah, but in the leaf, not on the leaf. If it goes in, you do definitely see a thicker leaf and you see a denser waxy layer.
You see all that, but you see
which is
all
what
that.
You need, that's what we need.
Yeah, but it doesn't you're right, and I've you know, it won't go down, and also you've got no root in. In other words, the holes on a plant surface are not as efficient as taking up chemicals as the roots. So you have to think about it. You have to think. I'm not, you know, I'm not coming here with all the answers, but it's worth. But I think it's important that you understand this when you use it. In a sense.
We've got about another 5 or 10 minutes, something like that.
That's all right. So what about other crops? This is really quick. We've done work on courgettes. It works completely well, does exactly the same things. And I have, and I've collected together some of the other things which I think you'll be talking about later. Cabbage stem flea beetle, definitely inhibited by silicon. I've tried...
Sorry, you might be just about to rush past one that's really important. There's no doubt about it. Where I use a lot of silicon on a regular basis, I believe I am seeing a reduction in slug damage. What would you say on the... Can you...
Yeah, I've got... Yes, the trials, I didn't do these trials. There is definitely a reduction in slug damage, but I think probably both cabbage stem flea beetle and slug damage is reduced because of the physical effects on the leaf surfaces, however you've applied it.
We're being told, and again, somebody in a similar line to yourself is suggesting that the silicon applied as a foliar makes the sap unpalatable to the pest, and they go. And I have sprayed it onto crops, and within 24 hours, a crop that was black with cabbage stem flea beetle, there's not one there, and they have no... Don't panic.
I think you're right, and certainly for the slugs, the plant becomes unattractive. They don't feed as often.
But that's what we're finding with the cabbage stem flea beetle.
Yeah,
it doesn't kill them.
Well, it's not meant to. No, I'll rephrase that. It is not a pesticide. That's the whole point of my talk. It is not a pesticide. You are modifying the physiology. However, I'll whip through these because you might not, but certainly winter wheat, it works, and broad beans and sugar beet. So what's my overall summary? I hope this is right. Majority of crops will benefit from the application of a silicon nutrient, right? And I really believe that. The literature is now moving from saying it's non-essential to saying it's, wonderful word, quasi-essential. But I don't think that'll get it into the United States, because the United States won't let you have things which are not actually essential. A frequent application is most efficient. Passive defense pathway is definitely enhanced by the use of silicon nutrient. There are other benefits, including yield. I think if we did the research, we would find that there is also a benefit to the active defence pathway, but I have not done the research.
Could you go back to the wheat slide?
Oh dear, what have I got wrong in my wheat slide? I didn't say it was wheat. I said, what was your question?
Oh, I just wanted to read it. You went through.
Oh, sorry. So what we've got on the slide is there was an increase in chlorophyll when sprayed at T2, which we did the results of. Urofins showed silicon accumulation doubles in winter wheat with a spray. And there's an increase in yield, that was urofins. A reduction in aphid damage, that was in published literature, and reduction in time aphid spent feeding, that was Harper Adams did that, and Redding did drought resistance or resilience, and there is evidence for that, yes. Sorry.
I've got a random question for you. So we've made this plant more resilient to disease and to pest. What happens with the straw? Is it a slower breakdown when you've got the straw at the end of the season? It doesn't matter to anything, but it was a question.
Well, no. Two things. Do you know, but just before I came away, I looked at my bookshelves and realised I'd got a massive book from a conference all about straw decay. I think it was the 70s or 80s. We had somebody from the days when there was weed research at outside Oxford. We had somebody from Hatfield working on straw decay, and I think it might influence it, because, very interestingly, the courgettes that we've just done, what we found, we haven't done the statistics, and it's going to have to be a completely new experiment next year. What we found was that the silicon-treated plants took slower to dry in the oven for our biomass research than the ones that were not treated with silicon. So it could slow it, but perhaps you can't, we can do the work. But I don't know how serious that, how quickly do you want your straw to break down? Because I was looking at all this stuff that Erna Grossbard did and thinking, actually, everybody said what she was doing then was rubbish, and now we want to know. I think she was asked whether if you sprayed herbicide, whether it would control plant diseases on straw, the eye spots of this world.
You can probably use less fungicides because you're not...
Oh, absolutely.
Absolutely. Your plant, the straw should break down quicker because of the lack of the fungicide. So there'll be a sort of a plus and a minus to it, maybe.
Double-edged sword.
Yeah.
Agriculture.
Yeah. And I suppose that's the end, isn't it? Yeah. And I suppose that's the end, isn't it? In the sense that you really have to think about the interactions as well as what you're doing. You have to think a bit and try cautiously. Not if it's been deposited in the straw. Not if it's been deposited in the straw. That's locked in. And so it would only be available if something was able to and the chemical reaction made it re-available. There is a thing, actually, that's not all laid down in a crystalline form, and it's the crystalline form which is most protective. If it's laid down in a much more general form, what the literature calls amorphous, then it's not as effective, and that is what happens in some species.
various types of trichoderma to break it down. So if we did that, that would release the silicon to make it available, wouldn't it?
Well, that depends. It's a chemical. Well, that depends. It's a chemical reaction that's going to make it available to turn it into salicylic acid. Should you want to, I have got a poster with me that you can have a copy of, which gives you the pictures for the 2 spotted spider mites. I'll stop. Thank you.